Hello and welcome to this video. In this video we will study the course number theory, and we will show that the Bell ordering principle is actually equivalent to the finite principle of induction. Principle of finite induction. Okay. Let's take it in the form of theorem. The statement is as follows: the Bell ordering principle is equivalent to the principle of finite induction. Okay, start the proof. We shall prove that Bell ordering principle implies second principle of induction, and second principle of induction implies first principle of finite induction, and first principle of finite induction implies Bell ordering principle. So it means they all are equivalent. Okay. Suppose Bell ordering principle holds and a subset S of the natural number satisfying 1 belongs to S and 1 to up to so on K belongs to S. This implies that K plus 1 belongs to S. Now we have to show that S is actually equal to set of natural numbers. Okay, assume on contrary that S is not equal to set of natural numbers. Okay, then T, we consider another set T, which is actually set of natural number minus S, because we have seen that S is, we have considered that S is not equal to N. It means whenever we will take the complement of S, then we will get another set T, which is definitely non-empty set. Okay. By Bell ordering principle, T must have a least or a smallest element, say M. Okay. Now because this M belongs to T and T is actually the complement of S in set of natural numbers, so this M does not belong to S. This means M must be greater than 1, because we have seen that 1 to K are in S. Okay. Also M minus 1 will be greater than 1, because M is greater than 1, and that will be M minus 1 is less than M. This means this M minus 1 does not belong to T, because M was the least element of T. So M minus 1 does not belong to T, and anything which does not belong to T, that belongs to S. So M minus 1 belongs to S. Okay, we move further. This means anything which is less than M minus 1, M minus 2, m minus 3 up to so on 2, 1 belongs to S. Hence, this m belongs to S because of the condition 2. Whenever this also m minus 1 belongs to S. Whenever the integers 1 to k belongs to S, this means k plus 1 also belongs to S. And now we have seen that the integers from 1 to m minus 1 belongs to S. Then well-ordered principle m belongs to S, which is contradiction. And this contradiction arises because we have considered that n is not equal to S is not equal to n. Therefore, this S is equal to n because our supposition was wrong. Clearly, we have seen that second principle of finite induction is equal to principle of finite induction, first principle of finite induction. Now, suppose first principle of finite induction or principle of finite induction holds and S is a non-empty subset of non-negative integers if 0 belongs to S, then nothing to prove. Suppose 0 does not belong to S, and now we have to show that S satisfies the well-ordering principle because we have considered that the first principle of finite induction holds. Okay, and let T we consider a set which consists of those m which are from n such that this m is less than or equal to S for all S belongs to capital S. 0 belongs to S means S contains all the elements of n. So, okay, since for each positive k such that k is greater than or equal to 1 and S is subset of set of natural numbers, therefore 1 belongs to T. Okay. Now this means T is non-empty. Also, T is not equal to complete set because for any small t belongs to S, then anything which is greater than t, that is t plus 1, does not belong to capital T due to the definition of t, because t consists of all those elements of S of n which does not belong to S, which are smaller than every element of S, and this t plus 1 is greater than t, which is t is element of S, so t plus 1 must not belong to capital T. Hence, the condition 2 of principle of finite induction, or first principle of finite induction, is violated. Now we move further. That is, there exists an integer m belongs to T such that m plus 1 does not belong to T, this means this m will be less or equal to S for all capital S belongs to S. And because m is smaller than all element of S, and if this m does not belongs to S, then clearly this equality cannot hold and m will be strictly less than S for all S belongs to capital S, because if the equality holds, this m can belongs to S. Okay, this means the element which is the integer which is greater than m, the consecutive integer which is m plus 1, is less or equal to S for all S belongs to capital S. This means this m plus 1 also belongs to T because of the definition of T. T was the set which consists of all those elements from natural number such that m is less than or equal to S for all S belongs to capital S. Here this m plus 1 satisfies this condition, so m plus 1 belongs to T, which is contradiction to the fact that this m plus 1 does not belong to T. And this contradiction arises because we considered that this m does not belong to S. This means this m belongs to S, and m is the least element of S. Hence, well ordering principle holds. And that's all about today's video. See you next time.